Here's my mouse pointer. Oh, this might actually work. I'm on Linux, so this is a miracle already. Hi, this is CoreCLR 3.0 Intrinsics. I'm Dan, aka Damage Boy. I'm on these very fine platforms under that nickname. You will see a much more detailed version of this talk, around 10 times more content, I guess, on my blog in about a month or so from now. But for now, in my day job, I'm a CTO for a high-frequency trading firm. So that actually means a lot of things in many different contexts. But in our context here, that means that I'm part of a team that gets to make more money when we succeed in making our code run faster. Other than that, I'm an old-time Unix programmer with a passion for low-level and performance. I've done Windows and Linux kernel programming in my past, and I've even been privileged to be a part of this amazing team 15 years ago that wrote a really wacky hypervisor. That was also traumatic. Why are you here, really? So, there's this version of a talk or a speaker that comes on stage and gives you these rosy pictures of the future and tells you these bright, insightful things about how everything is going to be amazing. So I will give you the Eastern European version of my ancestors of this introduction, where basically a total stranger walks up to the stage, that's me, asks the organizers to lock down the doors and tells you how everything is basically horrible, it's all falling apart, and we're all going to hell. Right? So with that in mind, here is the last 40 years or so of single-threaded performance improvements in various CPUs. Each point here is a CPU that was somehow released somewhere in history. So after about a very happy first quarter of a decade or so, where we're seeing year-over-year improvements here of around 52% per year, again, we are finally hit with this ever-increasing slump or slowdown in single-threaded performance improvements as we are hit with these various limitations like Dennard scaling, Amdahl's law, et cetera, et cetera. Now, all of this is happening while transistor count is still doubling every 18 months, sorry. And finally, we're hit with what is today referred to as the stagnation or the death or the slowdown of Moore's law around 2015, where we're finally at 3.5% of improvement per year, which is really, it's next to nothing, right? So obviously nobody knows anything about the future, least of all me, but I think we can all agree that, the present basically sucks, right? So I found a very insightful quote that explains some of the reasons or the background behind this. I wish I'd thought about this 10 years ago, because it would have made things much more simpler. But this is by Jim Keller, who is this amazing CPU architect. He gave this ironically titled talk called Moore's Law is Not Dead, where he basically says that the reason we're seeing this slowdown from 2003 and onwards is it's all about unpredictability. Okay? And he goes on to say it's about branch, data, and finally instruction unpredictability. Now, I won't have time to go into all of this, but I do want to put some emphasis and some explanation or put an idea of what really branch prediction or branch predictability means. So at any given moment when our CPU, where a single core in our CPU is executing what we think is one instruction, it's actually executing hundreds of instructions into the future, right? It's starting to execute hundreds of instructions into the future in order to give us this performance that we'd like to have. So in order to do that, it also has to guess when it encounters branch instructions. So the machine code behind our ifs, our whiles, our for loops, when it encounters those instructions, it has to guess which branches are taken or not taken, right? Now, normally, it actually does a pretty good job at this. That's why we have these units in our processors called branch predictors, and they're pretty awesome. But when it fails, right, ultimately, it's not a god. It's not impervious to failure. So it can and it does fail. And when it fails, we or our code gets penalized. So on a modern Intel CPU, for example, that means that we get a 15 cycle penalty whenever we mispredict a branch. Just to give you like a number to keep in your head. So this is even sadder than what it might sound. To me, this already sounds very sad, but this might be even much more sadder if you consider that a lot of times the code behind the branch, so the code that we were either about or not about to execute, is more often than not, it's 1 or 2 cycles. So we get penalized with 15 cycles for guessing wrong whether we're about to execute 1 or 2 cycles, right? So branch prediction is a big thing. But it's only one thing. But for now, I hope I have you scared or at least motivated enough so we can, get to the next part. So, what really are intrinsics? So intrinsics, which are new now in CoreCLR 3.0, are really fake function calls that we get to call from our code, which the JIT comes in and translates them into straight machine code, right? So you can really think about this as we get to be assembly programmers by calling these fake functions, right? We're just going to call functions, but instead the JIT will shove some specific instruction per function into our instruction stream. Okay, so we get the privilege of going back to being assembler programmers. But really, why would we want to do that, right? I mean, we spent a lot of years getting away from that, so why come back to that? So really, our CPUs have inside them a lot of functionality that is really not easy to map into our existing languages, right? So a lot of very special instructions that simply do not look well in C#, or you cannot put them as keywords, it wouldn't make sense. So these things range from atomic operations, which some of you have already might have used, and these are already in effect intrinsics, going into system programming versus various kernel stuff, things like cryptographic instructions, so you can make the CPU do crypto for you. All kinds of wacky niche instructions. There's honestly funny stuff in there, but mostly this is about this concept, this new concept called vectorization, right? So I actually bothered to go and count this. Intel provides us with 1,218 intrinsics in their CPUs, and 96% of those intrinsics are all about this concept of vectorization, right? I even gave it 3 colors, so it must be important. So these are actually instructions that work on vectors, right? So just to give you like this short visualization of what this means, right? We have in our CPU a vector. Somewhere in our CPU we will have a vector with, let's say, 8 elements with these numbers. We have another vector with 8 copies of the number 10. We tell the CPU through an intrinsic, do this multiplication thing, and we get 8 results in one operation with these results, right? So normally, most intrinsics in our CPU take around, anywhere between 1 and 3 cycles. And I think that's already kind of like sets the expectation of what we can get here, right? We can do 8 operations, and sometimes even more, in a very, very short amount or a very small amount of cycles, okay? So, what are we actually going to do here? So, I think that every programmer should probably take a stab at sorting numbers at some point in their life. For me, that moment came a while ago. I got nerd-sniped into doing this horrible thing. So basically, I thought to myself, I'll take this really queen of sorting algorithms, Quicksort, which really is array.sort, right? It's pretty much what array.sort in C# does. It's pretty much the same thing. I'll rewrite this with vectorized intrinsics, and really, how hard could it possibly be, right? I mean, I even found some academic papers that kind of like led me into this and gave me a good starting point. So it's been 5 months since that moment. Honestly, I'm still having too much fun with this. It's not that I can't finish it, but I guess I don't want to. Probably. So yeah, so it's been a long time. I'm still having way too much fun with this, but So I have something that's roughly 6 times faster than array.sort. Okay, enough chuckles. So why did I choose Quicksort, really? So it's universally known, right? A lot of people know what it does and how it works. It's pretty simple to explain, which I will quite shortly. As we will see, and more importantly, we will see a non-trivial use of vectorized intrinsics. Okay, so we'll see something like it's real. It's not like, oh, take this bunch of numbers, multiply them by 10, 5 lines of code. Good job, guys. Let's move on. It's going to be challenging. I hope to see a lot of head scratching. I hope to see, I hope to frustrate you, basically. So, again, it's pretty close to array.sort. So I didn't pick this sorting algorithm from Stack Overflow, copy pasted, and oh, I beat that. How fun! I'm really taking the actual array.sort, which is, by the way, implemented in C++. It's compiled down to with a C++ compiler, and that's my competition here. Okay. So quick refresher of what Quicksort does. It's a divide and conquer approach to sorting. So in other words, it's recursive. It does sorting with n-log n comparisons to sort huge arrays of numbers. And more importantly, in this context, it performs what is called an in-place sorting. In other words, if we have, let's say, 10 gigabytes of numbers, we don't need to allocate more memory in order to sort that data. We simply sort everything inside our existing array. Now, while this is amazing as a feature to provide to users, when you're actually trying to do this quickly in your code, this poses quite a lot of challenges to write this. More specifically, we start by picking what is called a pivot value in Quicksort. So really, in this case, I simply copy-pasted the code from CoreCLR. Whatever they did, I literally copy-pasted their function. That's it. We proceed and start doing the real thing here. So the real thing is Partitioned D Array. What is really partitioning? We take the pivot number and we take all the other numbers. Then we rearrange the array in such a way that all the numbers to the left of the pivot, in no particular order, are smaller than the pivot. Then we have the pivot. We place it at that position, at the next position. It's never going to move again. It's there for the rest of the sorting operation. And then all the numbers larger than the pivot are on the right of the pivot, again, in no particular order. Okay? And we then proceed by recursing to the left and recursing to the right. And this is basically it, right? This will sort millions, trillions, no matter how many numbers you give it, this will work. Okay? So visually, I wanted to provide yet another visualization of this. So this was actually done by Michael Bostock, who's an amazing visual guru on the internet. And he basically did this visualization where we want to go from the top row of unsorted sticks to the bottom row where everything's nice and sorted, right? So each stick there is represented by a degree between -45 and +45 degrees. That's the value of the number in our array. And we sort this whole thing by picking a pivot value and assigning a pivot element and assigning a red color to it. And then we will rearrange the array around that pivot value, at which point it will get a green color. Okay? So this is like the introduction to the visualization, which is here. So what we're seeing here, actually kind of like, let's see if I can get more lucky. Yeah, that's more like it. So we start by picking a pivot number. We rearrange the array, so all of these sticks are smaller. They slant to the left of this value. All of the numbers here are bigger, so they slant to that side. And this is the final resting position for that pivot, right? It moved over here. Next, we recurse to the left, so we pick this element. It moves over here. then this is a very small partition. We recurse to the right. We pick that element. That element moved over here. Again, left, right, and we see that as we progress from from top to bottom, the array becomes more and more sorted, obviously, and more elements simply have this green color, right? So basically everything until basically all of our elements are pivots, at which point the whole array is sorted. Okay? You're with me? Okay, great. So another way, and an important way to, again, think about this is by collecting statistics about these sorting operations. So I bothered to collect all kinds of statistics. This is just a small sampling of them. Specifically, let's focus here on, let's say, the 1 million column. So to get 1 million numbers sorted, an array of 1 million elements, we end up doing a recursion depth of around 35 levels deep. We do around 340,000 calls for the partition function, right? So we're going to call that function a lot of times on different segments of the array, and we're going to perform around 13.7 million comparisons in order to get that original 1 million numbers sorted. Okay, so there's a lot of work here. And this is pretty much top of the line, right? There's nothing that can be done in sorting that's radically better than this. In terms of how this looks in code, this is pretty much the CoreCLR code lifted and maybe cleaned up a bit just so it fits into a slide. So what we do is basically we go from left to right. We look for an element that needs replacing, and we find that element. Sorry, we look from the right to the left, looking for an element that also needs swapping. So larger than, smaller than the pivot. When we finally do that, when we finally find those two elements, we swap them, and the whole thing simply continues until we run out of elements in our array, right? So immediately we can see that there are 4 branches in this code, right? So every while and obviously the if, they're all branches, okay? But not all branches are created equal, right? So these 2 branches are super bad for performance, right? Because they're actually reading data from our array, and keep in mind, the array is actually unsorted, right? We're feeding the CPU here with branches based on random data. It's just full of crap from the standpoint of the branch predictor, right? And while, for example, these 2 branches are actually not that bad, right? Because most of the time, if we're sorting a large array, this branch will always go true, 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 and we'll simply get into the code that executes it. So this is pretty easy to predict. This is pretty bad to predict. This is not our enemy. This is our enemy, in other words, okay? So that's all I have to do with the scalar version of quicksorting, or the non-vectorized version of quicksorting. So really, what is our plan from this moment onward? So we're going to rewrite or redo the partition function with this new concept, which is called vectorized intrinsics. Or we're going to use these intrinsics, which are now finally also available to us in CoreCLR 3.0. So which intrinsics do we use, and how do they work? So really, we need to figure out, how does an instruction really work on a vector? Does that really mean that we give the instruction a pointer to memory and it simply does its magic directly on memory? So to that, the answer is, in general, no. Okay, we have to understand this new concept, which is called vector types. Or in other words, in C# now, we have this new primitive type, really. This is, I think, the best way to think about it. We have new primitive types which are vectorized. Now, these special or primitive types are also supported, of course, also on the CPU level. So at the CPU level, they're exposed to us as registers, right? So we see new registers and we see new vector types at the C# level. And another important thing to keep in mind is that these registers have a constant size, which is normally described in number of bits. Okay, so in C#, this gets manifested or expressed to us through these new vectorized types in CoreCLR 3.0. These are vector 64, 128, and 256, and they are generic on T. Now, I did say they are special, so it's not just any generic type. It's not a normal generic type. You can't just shove anything you want here. You cannot use vector 256 of string, for example. T has to be a very specific set of primitive types. So as an example, we'll take vector of 256 of T, in which case we can use any of these. So these are the integer types, right? Byte, short, int, long. They're unsigned counterparts. And we also have float and double as the floating point versions. Now, in each of these cases, the vector of T will contain either 32 elements of 8 bits totaling in 256, right? So this 256 is really this 256. That's what I meant. Or for integer, which is really what we'll be using for the rest of this talk. So keep that number 8 somewhere in your minds. So we will be seeing a vector of 8 elements of 32 bits, or an integer, again totaling in 256 bits. Okay? So this is the right moment to start talking about the actual intrinsics that we will be using, right? So we need to understand these Lego blocks, these new Lego blocks, for most of you at least, that we're going to be building our partition function from, okay? So the first one, we'll start off with a couple of really simple ones, is vector create. So we'll see this in a second with more detail, but basically this accepts a single primitive value, and it simply copies it or broadcasts it into an entire vector. So really a scalar to vector operation. So the way this is expressed in C# is we provide the vector 256 create function with some value, right? And we get some vector in return, right? Pretty simple from the C# perspective. In machine code, this is actually one of the few instructions that gets, or the few intrinsics that gets translated into 2 instructions. This almost never happens. And in terms of visually speaking, this is what it does, right? So we take a single value and we can simply kind of like broadcast it, copy it, in this case to 8 elements, right? So this one is pretty simple to start with. Next, we have something that's still pretty simple and pretty, you'd expect to have this, right? We are about to sort millions of numbers. Obviously, we're not going to do everything just like with one vector of 8 elements. We need an ability to read data from memory and write it back into memory, right? Those are very basic operations to have. So that is done with both with load and store. Again, in C#, we have to use unsafe pointers. So this is maybe a good moment to just mention the fact that everything that has to do with intrinsics works with pointers when you're dealing with memory. There's no support directly for arrays or spans or anything like that. We're simply providing everything with unsafe pointers. So we have some integer pointer pointing somewhere. We call this weirdly named load DQU vector 256. Doesn't matter really why it has such a weird name. We provide it with a pointer, right? And we get some data in return. Conversely, we can store data by providing a pointer and data, and this will get data written back. Machine code, again, pretty simple. We're reading from a pointer into a register vector, or we're writing a register vector back into memory. Visually, again, we're simply providing a simple pointer to a start of an array, and we get 8 elements from that point onward copied into our vector. I didn't provide the store animation, but you can pretty much understand where this is going, right? So again, still pretty simple. This is where things are getting slightly more spicy, okay? So we can also do stuff like compare greater than. So this instruction, for example, takes 2 vectors, so 2 different vectors, and performs a comparison operation between them. So it does an 8-way comparison between 8 elements to a different set of 8 elements, and we get a third vector in return, where all the places where the comparison was successful are marked with a -1, and all the places where the comparison was unsuccessful are marked with 0. Okay? So again, from the C# perspective, pretty simple. We provide a data and comparand to our compare greater than, so we provide 2 vectors to perform the comparison, and we get a result back. Pretty simple as well on the machine code side, and visually we're going to compare, let's say, 11 to 22, right? We're going to compare 31 to 21, 69 to 22, etc. We get 8 results, and in the form of a vector, this looks like this, right? So I chose to represent -1 in the hexadecimal form, so the 2's complement version, so 0xFFF, right? So this is our result. But what do we do with that sort of result? So this is where a very important and common intrinsic comes in, and that's called move mask. So move mask is really, you should think about it as the reverse of the broadcast operation, of the create operation. Okay, so it takes the most significant bit out of each element, so 1 bit out of 8 elements, and simply compresses them down into a single scalar value. So again, in C#, pretty simple. We provide data to move mask, and we get an integer. Notice that this is a scalar result, so a normal primitive integer as a result. Pretty simple as well on the machine code side. And visually, we take these bits and we simply shove them. Now, to be completely honest, I'm lying at this stage because the bits are supposed to be in little endian, so it's supposed to be in reverse, but I didn't want to ruin a perfectly good animation, so I just did it this way. We are almost done with the list of intrinsics. The next one is a pretty simple one. We simply provide a number, any number, to this pop count intrinsics, and it counts the number of 1 bits for us. Okay? So in this case, 1, 2, 3, 4, 5, 6, 7, 8, right? And you'll have to trust me that the result that we're going to get is actually going to be 8. So again, pretty simple on the machine code side. It's a one-to-one mapping, right? We're back to being assembly programmers. Finally, I kind of like saved the most trippy one for last. So this is an 8-way permutation, or really rearrangement of a vector, right? So we can provide a vector 256, and we can provide a new order for that vector, and we have a single instruction that will simply do this rearrangement for us. So again, on the C# side, it looks pretty simple, right? Data, permutation, and we get a vector as a result. Machine code, also pretty simple, but here we're providing a, so we're providing a vector with the numbers 100 till 107 from left till right, and we're providing a permutation order, which is the numbers 0 until 7 to 7 from right to left, right? So essentially, we're creating this cross-hatch pattern, whatever you want to call it, right? So this is us telling we want to put in this position, we want to put this element. In this position, we want to put that element, right? It all kind of like makes sense to you? Good. So once we start executing this, this is simply what happens, right? So this is pretty neat, right? We got to provide some crappy vector to another crappy vector, and we got in return a completely reversed array, and this took, like, this is maybe important to say, this took 3 cycles, right? So on a 3 gigahertz machine, we can do this thing within 1 nanosecond. You would not be able to do this with normal scalar code, right? And it's impossible to do it at those speeds. So we finally kind of like have, I think, enough explosives, right, to blow this joint up in a way. So, or if we want to do it less violently, we can finally do a vectorized partition block, right? So we're going to discuss this short, super short piece of code that gets 8 elements repartitioned within a single vector of 256. So those primitive types that we mentioned before. We're going to see a load, followed by a compare, a permute, and storing back the data into our array because we're doing in-place sorting. So how does this whole thing work? Right, so we select a pivot to begin with, right? Let's say I selected the pivot 100. Doesn't really matter why, it's just a number in the array. Okay, so far so good? Okay, so we proceed to create a vectorized pivot, right? So a vector copy of that pivot, so really 8 copies of this number 100. That's pretty simple as well. We load some data from our array, okay? So that means that now we have the following numbers: 111, 222, 323, and then the rest of those numbers, right? So this is the random data that I loaded from our array. We call the compare greater than operation. So we can perform a comparison between our data and our vectorized pivot. We get 8 results in return, right? So we get this weird mask in return. And this time I didn't lie, we call move mask, and we get this result, right? So the 3 top level bits here ended up on the left side here, and these bits ended up here, right? So this is our integer value, which really represents the top level bits of each of these vectorized elements. So now we have really this thing, and which is really the number 7. Okay, but now what? What do we do with this thing? So really, you can think about this mask, this number 7, as a number which really tells us where each element should go to, right? So what we could do, right, we could simply loop over the bits in the mask. We could read them one by one and say, oh, this is small, this is 1, so it goes to the right. This is 0, this goes to the left. We could do that, but then we'd be back to square one, right? We'd be doing basically 8 branches based on 8 random bits. Obviously, I did not fly to Poland to talk about this, right? So what we are going to do is something pretty different. We're going to basically create a pre-computed permutation table with 256 entries, okay? So each entry is going to be 8 elements, and those 8 elements tell us how we want to rearrange that data inside the array, okay? And inside the chunk of the array that we're looking at. So again, we pre-compute all the permutations ahead of time. Basically, I have a unit test that just dumps it into the screen, and then I copy-paste it to my source code. Each permutation entry provides the correct order, and the table is simply embedded in the source code. That's all there is to it. Here are about 4 entries that I wanted to show you out of the 256. So we'll start off with a couple of super trivial ones, right? So in case our mask was all 0s, or in the case that our mask was all 1s, let's go back in our heads what this really means. This means that all the numbers were smaller than the pivot, right? Or in this case, all the numbers were larger than the pivot. So really, in both of those cases, there's no reordering that needs to happen, right? If all of the numbers are smaller than the pivot, we can just keep them as they are. There's no reason to do anything here, and we don't. So we simply provide the numbers 0, 1, 2, 3, 4, 5, 6, 7, and the order is kept as it was before, right? Nothing happened. We didn't touch anything. For the value 7, which as luck would have it, I had it in my animation. So in this case, right, the 3 leftmost, I know I'm pointing to the right, I'm not having a seizure here. So the 3 leftmost, remember this is little endian, so the 3 leftmost elements need to go to the right, and these 5 elements need to go to the left. So the 3 rightmost elements are going to be 0, 1, and 2, and the elements 3, 4, 5, 6, and 7 go on the left side, right? And this repartitions this specific case. Again, we have 256 of those. The last one that I'll show is the case where all the odd numbers need to go on the right. Sorry, all the even numbers need to go on the right, and all the odd numbers need to go on the left, right? So this checkered bit pattern is actually the number 170. So we get to see 0, 2, 4, 6 on the left and 1, 3, 5, 7 on the right, right? So it's pretty simple. You can imagine that there's a table with 256 of those, and now we can actually use them, right? So how do we use them? So we actually do this operation, right? So we load from the permutation table. We use the mask that we just had, right? So this number 7, now we shove it in here. So it's basically an offset to the beginning of our table. We multiply everything by 8 because We have 8 elements per entry, blah, blah, and we load the permutation entry, right? So the same 0, 1, 2 that we saw in 3, 4, 5, 6, 7, they're back here. And now we can basically tell our processor, do this for us, right? So we permute the vector, and we get a permuted version of our vector. So this is really partitioning, right? This is what partitioning means. We just did it, but we did it within a single vector, okay? So moving on, this is how this basically looks in code. So we have somewhere in the top level of our function, we have this call to vector.createPivot. We get our vectorized pivot. We call the load_dq vector on some pointer, which we'll discuss this whole where we read data from in a second. We get data back. We call, sorry, I should have done this simply. So, right, so we load the data. We then proceed to do compare greater than. Once we do compare greater than, we get that 8-element mask. We compress it down to a single, in this case, uint or integer, basically. We, again, take this mask and put it in the permutation table as an offset. Sorry, we provide it to, together with the permutation table as an offset to the load operation. We call permute, and at this point, basically, we have a completely partitioned vector. Obviously, it's not done yet, so I'm going to show some code that I'm going to refer to in a second. We write the data to the left side of the array, we write the data to the right side of the array. You'll see what this means in a second. And we need to remember how many bits were on each side of our partition, so we call this pop count operation. So pop count, I remind you again, pop count counts the number of 1 bits. So really the number of 1 bits is the number of elements that went to the right hand side of the vector, and the number of 0 bits is simply 8 minus that pop count, so that's the number of elements that went to the left side of the array. This is all there is to it. Now, one thing to keep in mind here, again, referring back to that discussion, there's one thing that we're not seeing here, right? And that's branches. There's not a single branch from top to bottom in this piece of code, and it will get 8 elements partitioned inside the CPU, right? We didn't see a single branch here. This is really why I did fly to Poland, okay? So, so now we have our vector partitioned, so what do we do next, right? So we're not done yet because all we did is mess up my slide, but all we did is really we just generated a vectorized 8-element partition. So the idea is that we will read 8 elements at every iteration and then write 8 both to the left and to the right. And we need to remember that allocation is bad, right? So we can't just do anything like that. So there's a problem here, right? We're reading 8 elements from the array, we're partitioning them, and I've been saying twice or 3 times here that we're writing it both to the left and both to the right. So it seems like we're writing more data than we're reading. So what we actually do is we make some room in our array. Suddenly it turned on. Okay, so we make room inside our array by basically cheating a bit, right? We stack allocate some memory, around 2 elements of vector 256. So in total, we allocate 64 bytes, and we use those 64 bytes as slack space. So we kind of like read data from an array, shove it into the temporary memory, and then we can basically do the following thing. So this is this is my approach to the outer loop, right? So we've made some room in our array on the left. We've made some room on our array on the right. This is simply data we copied away, so we would have space to write into. So once we have that, we can proceed and read some value. Now, initially, it doesn't matter if we're reading from the left or from the right, so we just read, let's say, from the left. We have this data. Now we run our vectorized partition block, right? So we take those 8 instructions or so, and we simply run them on our vector 256 element. So we get something partitioned. In this case, we got a 3 to 5 split inside our vector, right? So we see there's 3 elements on the left, 5 elements on the right. Once it's done, we write it to the left side, and we do the pop count to remember how many elements were on the left, so we don't care about those anymore. We do the same thing on the right, count again, and we know now that we have that. Now, at this point, right, we chose to read from the right side. Why did we choose to do that? Because now we have less space on the right than we have on the left, right? Whenever we read data from the array, we have no idea how the partitioning operation will, what's the outcome of the partitioning operation. Maybe all of the elements need to go to the right. Maybe all of the elements need to go to the left. So we're continuously doing this cat and mouse game where we're basically checking which side is closer to getting overwritten, which side is closer to us writing over data that we have not partitioned yet. And then we read from that side that is about to get overridden, so to speak. So we read from that side, and by reading, we make some more room in it, right? And thereby we kind of like postpone the inevitability of running out of memory or running out of space. So again, we partition here, move to the left, move to the right, and again, we need to make this decision, right? It's still pretty clear that in this case, we need to read from the right rather than from the left, so we do that as well. We read some more data, partition it again. Again, this goes to the left, that goes to the right. At some point, of course, we continuously switch between left and right. So the way this operates is that all it does is continuously say, okay, left, right, left, right, left, right. Finally, we're just out of memory, and then the whole partition is simply done. Okay? So, second. Yeah. I think that was it. Wait. No. Okay. So, in summary, what I wanted to show you is a rather complicated piece of code that shows you how to really use intrinsics, which are now available to us in CoreCLR 3.0. I want to remind, sorry, no, this is the wrong slide. Now I finally understand what I messed up. I have 50 more slides ready for the next talk in case the speaker gets a heart attack or something. Sorry. Okay, sorry, of course, I forgot the most important thing, right? So, no, it's just messing up with me. Presentations, right? Never do them. Okay, yeah. So really what I wanted to show you finally is basically this is benchmark.net results for what I just showed you, okay? What we can see is that very quickly we get into a situation where our code is running much more faster than array.sort until we finally see around 1 million or 10 million elements are sorted at around a rate of 2.7 times faster than array.sort. Now keep in mind, array.sort is C++. We're using intrinsics in C#, but still we get this phenomenal performance, right? Now this is merely a starting point, right? If I want to translate this to where I am in my blog post, if you were reading this in the form of a blog post, then this is roughly halfway done. From here, I still have like another 3x speed up, and I don't know, maybe in a few more days I'll have some more. I really keep finding more stuff to do here. It's pretty shameful. But this is really our starting point. So we didn't beat unpredictability yet. There's a lot more stuff that needs to happen for us to really get this thing done. However, I want to summarize here just a bit. Maybe this time it will work. Okay, this is much better. Right, so I think that what I want you to understand is that we can and we should kind of like reapproach even age-old problems like sorting and try and find new ways to increase the predictability that we express to our CPUs. I think that by doing so with intrinsics is a very effective way because intrinsics inherently provide more predictability, and that's not all there is to it. But now this is finally available to us as C# and .NET programmers now that CoreCLR 3.0 is out, and be nice to your CPUs. Okay, that's kind of like what I wanted to say. Okay, so thank you.
Thank you very much, Dan. Unfortunately.